Okay, here we are. Okay, so every triangle has a special ratio inside of it, inside the line that is describing the height of that triangle. For example, we have a square here, and I'm going to be talking about the height of the triangle inside the square. All right, so the first thing that that height has is a half. That is always there, will always be at the same place. But this triangle also has a center point that is not exactly at the halfway point of that line segment, the height. So to find that, we obviously have to find the midpoint of the sides, which I already did. We then have to draw a line from this corner to that midpoint. And now we have our center mass, center point, center equilibrium balance point of that triangle. Okay, so every shape, every triangle will have this property right here. What we already have is a ratio. We have a half right here, we have a 1/16 in the middle, and we have 1/3 here. That doesn't change. Now, for example, this height is 60, so let's measure it so you know that this is a third. This is a 1/6, 1/6, and this is a half. Any triangle will have that property, all right? If we set this to 1, this will be a third, this will be a 1/6, and this will be a half. Doesn't matter. Now let's prove that every triangle has this special ratio, this special property in the height of it, all right? So now let's make this triangle different. Let's make this triangle bigger. All right, I'm going to extend this triangle to 70 right here, and then we'll go 70 down this way. All right. Now, is this ratio on the first height, is it going to hold? Is it going to be there? Is it going to be the same points that intersect this next one? We'll see. This next triangle, same height. We'll go to from this corner to this corner to the center, from this corner to the center, boom, same spot. All right. So a bigger triangle and its height still contains a ratio that starts with 1/3, 1/6, and a half. All right. And that all makes up the 1. All right. So let's make a smaller triangle now just to see if it holds. Right. We're going to make one that is smaller right here to the 10. Right. Same thing. I'm going to find the midpoint of that line. I'm going to draw my line segments from the corner of the triangle to the midpoint. Boom, still holds. All right, so this ratio that is inside the height of a triangle and the line segment or any side is always going to be present, and it's a ratio of 1/3, 1/6, and a half. It's always going to be like that. But now, in this same process right here, what I'm going to do is I'm going to find phi. Where is phi in this height? Where is it? I'm going to leave everything that we have right now, and I'm going to color the center red so we know that's red. I'm going to make it a little bit bigger so we can see it, and I'm going to color this guy blue, and I'm going to make it a little bit bigger. So that's the center point, and we have our balance point. Now I'm going to create. I'm going to look for phi in this height, in this middle line segment. All right. So first thing we start is we create a square because that's how we are told that we find phi. So we'll create a square, and I'm going to throw it in there. I'm going to find its midpoint. Everything is looking great so far. That's not it. Midpoint. And I'm going to create the golden ratio because the golden ratio is extremely tied to 1/6. But let's go. Boom. Now look at that. Look how close this lands from the midpoint of my height. All right. Now that's in any triangle that I do this process, it will be off from the center, from the height, from the midpoint of the height. All right. So we argue that, well, that's because the value is more and that right there is the halfway point. So that's 1.5 or, blah, 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 but it's not, right? The process that we just showed that contains all the ratio of the 1/3, the 1/6, 1/6, and the 0.5, it's inherent in all geometry. It's inherent in all the triangles. What we just did is not. But I'll tell you what it is though. If we do the same process for finding phi, but instead of using a square, we use an equilateral triangle, right? We're gonna do the same process I just did, but we're gonna use an equilateral triangle instead. Because the number system was based on the equilateral triangle, not the square, and this is the reason why. All right, we got that. We're gonna get the halfway point. I'm gonna, well, can't throw my line segment yet, so I need a few other lines. Let's put a perpendicular here so I can transfer. And there we go. Now I can. All right, got this one. We got this one. Now let's throw our circle in there. Boom. Where does it land? Of course, it's going to land exactly where it needs to be because this is the true golden ratio. The golden ratio is not derived from the square. It's derived from the equilateral triangle. As proof here, the equilateral triangle will give you both locations, the center of the height and also the balance point of that height. All right, you can do this in any triangle and you will see that this is how it is.